are two things, and I will mostly use the board. First is a continuum version, we call it hydrodynamics model, of essentially that corresponds and could derive from the Bicek model. So I call it hydrodynamic model of fluid, which is actually was first due to John Conner and Stein II, and was developed actually very shortly after Bicek proposes this discrete model. And then I will spend the second part of the hour describing a model of active colloids, so synthetic swimmers, if you like, modeled as self-propelled particles, which I think is very useful to sort of understand in a very simple way what makes active systems sort of different from a common equilibrium system. So let's start with the first one. Relatively recently, this continuum theory I will write down in a minute. So I'm going to write down continuum theory, sort of hydrodynamic equations, not unlike the ones that William Irvine was discussing last night, but for an active system. I will just write down the continuum theory, however, which is actually how Conner and II first developed. They sort of wrote it down on the basis of essentially symmetry considerations. However, more recently, starting in 2009, people have actually derived the equation I will write down, starting from the microscopic dynamics, going from sort of the microdynamics to the Boltzmann type equation, and then coarse-graining that to actually derive hydrodynamics. And if you do that, you actually, the various parameters in the continuum equations are expressed in terms of semi-microscopic parameters of the model. But I will not do that. I will just formulate it on the basis of symmetry, as you do for sort of all this type of continuum descriptions. So if you want to formulate a continuum theory to describe a system, you need to ask yourself, first of all, what will be the fields that you're going to use. If you are describing a simple fluid, you will use density, momentum density, and energy density. Why do you pick these three quantities? Because each one of them satisfies a conservation law, the conserved quantity. And conserved quantities are special. The dynamics is the dynamics is slow on large scales. And so you can kind of single them out. There is a separation of time and length scales in the problem. If you're interested in describing the large scale, the macroscopic physics, you can pick out these quantities that are spatial, sort of average out of the microscopic degree of freedom, and just look at their dynamics. So the quantities that are, I call them spatial or slow in some sense in macroscopic systems, generally belong to two classes. They are either associated with conserved quantities, or they are associated with broken symmetries. A magnetic system, for instance, that where the order state is characterized by a broken symmetry, the magnetization or the magnitude of the the direction of magnetization may be associated with what's called the Goldstone mode, meaning it relaxes at a rate, perturbation from the order state will relax at a rate because it is infinitely slow in the local plane. So we need to identify these quantities for our sort of model of flying spins that I discussed just yesterday. So first of all, I said the dynamics is overdamped, the system is moving on a substrate. So what are the conserved quantities? And I'm not going to be interested in energy. In this system, there's really no energy that you worry about in the problem. So what do you think, what are the conserved quantities here? Anybody willing to venture? So I said in a fluid, normal fluid.
Momentum.
Momentum, okay. Is momentum conserved? Things that are moving on a substrate, there is friction. Is momentum conserved?
The number of particles.
The number of particles that must be conserved, or the number of spins in this model. That's true. Anything else? Is momentum conserved? If something is moving on a substrate and there is friction on the substrate, the answer is no. You don't care about energy. So actually that's all there is. So our continuum field, which is conserved, associated with conservation law, will be the density. I will use the number density. I will call it rho bar. And that's my conserved field. In addition, these things, I call them flying spins, flying magnets. So there can be, we discussed last time, that there can be an order state where everybody is on average aligned in the same direction, and therefore, of course, also moving in that direction. And there is a disorder state. So there is the possibility of a phase transition, possibility of a broken symmetry. And if I want to describe that, I must incorporate here the order parameter of the field that might describe the broken symmetry. Now, that field, I could call it either a velocity or a polarization, depending on whether, it's certainly a vector field, but I could call it either way, depending on whether, in fact, I will see it has kind of a dual nature, and that's what makes the problem interesting. I would call it either way, depending on whether I'm interested in highlighting the fact that this order state is a moving state, or I'm interested in highlighting the fact that the order state has sort of a ferromagnetic order. So, for today, I will call it V for velocity. Okay, but in a lot of the literature, we also call it you see the same field called P for polarization. And if each particle, like in the Vichek model, is moving along at a speed V naught, actually the two are simply related in the sense that V is V naught P. This is V naught is a constant parameter of the problem, they really are the same thing. Okay. So what I want to do now is just write down on the basis of symmetry the equations for these two fields. But the equation for rho is very simple because V is the velocity, so rho V, just like in a fluid, is a current. Particles are conserved, so rho just satisfies the usual continuity equation, which I write here, that essentially number of particles in a region can only change if particles flow in or out of that region. So that's the equation for rho. It's really very simple. Now let me write down the equation for the velocity. The equation for the velocity will be sort of like an Navier-Stokes equation for a fluid, but with some differences. It accounts for the fact that this system can actually order, there can be a non-zero mean value of V, essentially, without actually applying any external forces. So let me write down that equation and then explain the various terms what they mean. I'm just going to write it down so that so it looks a little complicated, but when we look at all the various terms one at a time, you'll see that it's really not all that complicated. Okay, now let's not confuse this P with that P. This is pressure. And some terms I'm really not going to care about so much. So it's long. It's example called black dot, okay? If you didn't have this term, I'll use one of these pieces of colored chalk we have here. Okay, let's for a minute imagine we didn't have this term. Then the rest really does look sort of like an Navier-Stokes equation. An Navier-Stokes equation would have lambda equal to 1. Lambda equal to 1 is required from Galilean invariance in the Navier-Stokes equation, but here we do not have Galilean invariance because things are sliding on a substrate. So there's a preferred reference system, and so generally lambda will not be equal to 1. Okay? Navier-Stokes equation, this will be, K will be the shear viscosity. And here it could also be a shear viscosity if you think of this as a velocity, but if you think of this as a polarization, K is sort of like a Frank constant, actually, of a nematic liquid crystal. In any case, what this term describes is the fact that it costs energy. So say the system is in an order state, it costs energy to create deformations from that order state. Okay. This is gradient pressure that will be there in the Navier-Stokes equation. And these are sort of some more complicated, sorry, I wrote this incorrectly. correctly. That's what this is. These are more complicated. I would like to call them convective terms. Convective terms, this is a convective or advective, sometimes called term. One gradient and two velocities. These are also one gradient and two velocities. They are also convective terms of slightly different symmetries. If you like this, you could also think of it as a correction differential. And we're not really going to worry about them very much. But they don't have any strange structure. Still, the equation looks similar to Navier-Stokes equation. What is different is this term here, these two terms here. First one is sort of like a friction. After all, things are going to sliding on a substrate. The second one, actually, we'll see in a minute, actually sort of makes sure the velocity cannot get too high, provides like a limit to the maximum value of the velocity. But this term also, if you actually were to think of my order parameter as a polarization, or if you like, if you're more familiar, think of it as magnetization. Okay? What this term would be, this would be the derivative, maybe 1 over the kinetic coefficient times the derivative of a Ginzburg-Landau type free energy with respect to your order parameter. And as we'll see in a minute, this is the term that provides the possibility to go between the order and disorder state. Okay. Are there any questions about the equations so far? So, pressure, I haven't told you what it is. We are doing my white chart, but yeah, pressure in general, of course, will depend on rho, but it could also depend on v squared, because v squared is the magnitude of the order parameter. So it's a funny mixture here, the hybrid of Navier-Stokes hydrodynamics and Landau theory for equilibrium magnetic system. Okay? And this fact that the system has this hybrid nature gives you some curious results. Now, you're probably very familiar with the free energy, say, written for a magnetic system when you try to model a continuous phase transition. You would write it, and I'm calling my magnetization V, or polarization V in this case, okay? But you will write this something like 1f integral over R, some parameter times V squared, and some other parameter times V to the fourth. And then if you take the derivative, well, if you choose gamma equal to 1, so let's forget this gamma actually here, if you take the derivative, you get that. And this kind of free energy is the one you use to model the simplest type of continuous phase transition. Beta is assumed to always be positive. Alpha can change sign as a function of some parameter, often the temperature, but clearly not here, not the temperature. And your free energy, if you were to plot it as a function of V, for alpha positive, looks like that, but for alpha negative, has a solution, or two solutions, that correspond, supposed to be symmetric, that correspond to an order state. So the same thing will be true here, but the parameter we're going to tune here for alpha to change, we could think actually of two things. Remember last time, we could think of the strength of the noise, but in this context, it's probably actually easier to think in the strength of the temperature. So alpha will be a parameter that can change sign. So think of the density. Alpha will be a parameter that can change sign as a function of the density. Okay, so what can we do with these equations, or with any kind of sort of continuum model of this kind? Again, this is like Landau theory, only really, even though I wrote this down, I actually don't have a free energy for this system. I have to start with dynamics, and I will just look at the dynamics. But I'm going to do things not too different from what you often do with Landau theory. So what can you do with this? Well, first of all, you can ask, put it down. What are the stationary homogeneous states that this set of equations predicts for you? So what do? We kill all that hard derivatives, we kill all gradients, and see what are the solutions that we're left with. Well, clearly for the density, rho is to be constant, let's call it rho naught, okay? And then for V, the equations we have left is alpha plus beta V squared, V equal to 0. And this is precisely what you study for the magnetization in Landau theory. This equation you can show, it corresponds to that kind of picture that has two solutions. One solution is V equals 0, and that is the solution when alpha is positive. And the other solution is V equal to minus the square root of alpha over beta, and that's the solution with alpha is negative. So this is a disordered state. This is an ordered state, which is both a polarized state and a moving state. This is a spontaneous Broken symmetry. What is the direction of the velocity in this ordered state? What's the direction of the velocity in this ordered state?
Polarization.
What's that?
Polarization.
That way, that way, that way. No, could be that way, right? What's the direction of the velocity in this ordered state? Does it matter?
Any.
So we know the magnitude of the velocity, but all directions are the same. Okay, that's what spontaneous Broken symmetry is. And so we have this two-order state, and we have the transition from one to the other as a function of this parameter alpha, which again you could think of as changing sign as a function of density or as a function of noise, and indeed what you get when you derive these equations from the Vicek model itself. So the first thing we can do with this equation. What's the second thing we can do with this equation? Or what's the second question one may want to ask about these two states? Yeah.
If you perturb it somehow, what happens?
That's right. Or I could rephrase it, are they stable? Right? That's because actually in equilibrium, if it was an equilibrium XY model, this state wouldn't be stable. Fluctuations will be strong. Okay? So the simplest way to look at the stability of this state is the following. So let's take the order state, just because I'll tell you this one is stable. Okay? Let's take the order state. Let's actually call this V naught. Okay? And let me pick the direction of the velocity. Let me pick the x-axis in the direction of the mean velocity, for instance, just for completeness. So what I will do, I will say I have rho equal to rho naught plus delta rho, where delta rho is a fluctuation. I have V equal to V naught x plus delta V. I substitute these answers in those equations up there and linearize. That is, I throw away all terms that are quadratics or higher in these fluctuations, and I get a set of linear, I'm not going to do it because it's a lot of algebra, I get a set of linear equations in the fluctuations. Okay? And then, where would this fluctuation come from? Well, they could come, for instance, from noise. I actually could have added to that equation noise, which you do. Remember, these are phenomenological pictures. So one is actually being a little bit sloppy here about the noise, because I add noise to the nonlinear equations, and then I linearize. This is a little sloppy, that's why I didn't add it. But you have, or you could imagine fluctuations coming from an external perturbation, a field of some type, okay? And then you have to ask, how do they relapse? So you put them in the equation, you linearize, and then the simplest way to do this is to look for solutions for both of them that go, so remember, these are both functions of R and T in general. You look for solutions of the following form. Q is a wave vector, so effectively what you're doing is taking a Fourier transform. So say your gradients becomes IQ, your Laplacians become minus Q squared, and stuff like that. And then there will be some decay rate. These are linear equations, two coupled linear equations, actually three because V is a vector. And then you can solve them essentially for eigenfunctions, eigenvalues S of Q, and there'll be some linear dispersion relation for this S of Q. And then of course, S of Q general, these dispersion relations, which are like the dispersion relations for phonons in a crystal, say, right? They generally be complex. They might have an imaginary part and the real part. The imaginary, if they have an imaginary part, the imaginary part tells you that these are propagating waves, and they will tell you the speed of propagation. But the real part will tell you whether the modes are stable or unstable. Because clearly, if the real part of S of Q is negative, you're fine. The mode decays a long time. But if the real part of S of Q is positive, then these things blows up exponentially. And so what this tells you is that if you take your order state and perturb it somehow, the fluctuation will grow without bound, and so the order state is unstable. Okay? And in this system, something actually quite funny happens. There are actually instabilities. And so you started out writing down a model that has a continuous phase transition at alpha equals 0. You work this through, you find instabilities at a characteristic wave vector, Q naught, in this case, in the x direction, okay, right at the onset, right at your continuous phase transition. This instability at the characteristic wave vector Q naught, you actually show that there's an instability to what people call a banded state. Of course, this kind of analysis does not tell you what replaces your homogeneous order state. It just tells you that the state is unstable. However, if the instability has a characteristic wave vector, and if, for instance, it's a propagating wave or not, actually does allow you to make some guesses about the nature of the unstable state. And so the guess is that that combined with numerics, which of course will tell you what replaces this uniformly ordered state, tells you the instability is to a state where you have ordered bands, which I will draw like this, in an infinite system with periodic boundary conditions and so on. You have ordered bands that are actually traveling at a speed that is determined by a combination of V naught and that coefficient lambda that kills the Galilean invariance. So this will be a disordered region. And these are ordered regions. So the system is made up of bands traveling in that direction. So the system actually has coexisting ordered and disordered region, which is kind of a typical signature of first order phase transition. Now, what you would like to do, and nobody has really been able to do right now so far, this is an open question, is go back to the nonlinear equations and see how possibly the nonlinearity may be able to do something for you that changes your continuous transition into first order transition. And we've tried, but so far actually failed. So it's something that we could try to do. Yes?
So in these banded states, is it the order that travels across the cell, or is it the particles?
These are density, these bands are density waves.
Oh, okay.
These are density waves. This system, that's another peculiarity of this system, in a fluid, solid. Sound waves are density waves, and they come from the interplay of inertia and elasticity. Actually, within the fluid, because the elasticity from compression. Okay. This system has no inertia, so it shouldn't have sound waves. But it does because it has this self-propulsion, if you like. So these are sort of like sound waves in an overdense system. So they are density waves. Yeah.
So this idea that these banded structures are kind of a coexistent state, I mean, I guess is there a way to distinguish that from, say, a lamellar state of any static system?
So I actually achieved it slightly. It's more complicated than that.
Okay.
This banded structure could also be soliton-like states.
So they can exist independent of interaction.
And I should say that most of the numerics on the continuum equations have been done without noise. And in this case, this banded structure appear to be soliton-like states.
Okay.
In the numerics of the microscopic model, they really seem to be more like coexisting region. And people indeed have suggested that these may be what they call a symmetric type state.
Right.
Okay? But we have been trying to do something, but I haven't really gotten very far yet. Okay. Any other questions? I just want to tell you one more thing about this model, which I think is an interesting factor, which is actually which perhaps is not unrelated to this as a matter of fact. But, these equations actually, now they look complicated at first, but actually they're not very difficult, and they're extremely rich. They exhibit all kinds of unusual behavior. So they have these traveling sound waves, they have these continuous transition, which then seems to be destroyed and turned into first order transition right at the transition, which makes it very difficult to describe.
And what can be the expression of P?
P.
Yeah.
What do you mean? Can you ask me again?
Yes, which is a function of rho and V squared.
Oh, sorry, I forgot to tell you, the pressure. So the pressure actually, you can get so if you're doing this just phenomenologically, the way you've done here, you would just say to leading order, the V square comes from here, and to leading order, this term will just be proportional to that term. Okay? When you derive it from the V-check model microscopically, actually you find that the leading term in the pressure is proportional to V naught to delta rho. Okay? And then you could have delta rho squared, and higher order, you can imagine an expansion in the pressure in powers of delta rho, just like you do for any other fluid. This is kind of thing. Yeah, sorry, I forgot. Thank you. I forgot to say something about that. And actually, that term is very important. Because the coupling, so there's another thing I should say. So normally in a continuous phase transition, again, suppose this was a magnetic system, right? You tune the system, you drive the transition by, say, changing the temperature or even changing the density. But either way, these are parameters you change from the outside. You change the temperature and the system undergoes through the phase transition. Here, the transition is driven by the density, which is itself converted by the order parameter through the continuity equation. And that's what creates all this complicated, strange behavior. Okay, just one more thing about this kind of systems, this one in particular, is that they exhibit what people have called, I'll write it down here, giant number fluctuations. And I'm just going to tell you what it is without really going through. You can actually derive this again from these equations. Giant number fluctuation simply means the following. Normally, in a many particle system, suppose you were to take a subregion of the system and say that that subregion contains, so you have your system, here is your system, it contains a few particles. Now I'm going to take the subregion, and I say that that contains, on average, n bar particles. Okay? But there are fluctuations, so there are deviations. If I took an instantaneous snapshot of this subregion, the instantaneous number of particles n will be generally different from n bar. Okay? I will call this difference delta n. And then I can ask what is the variance delta n squared. Okay? And in a conventional system, so the root mean square variance of number fluctuation to behave like what? We put the, sorry, I want to put the one n there. So would that go like? How will it depend on n?
Like square root of n.
Like the square root, right? It would go like square root of n. That's essentially central limit theorem. That's what statistical mechanics is based on. Because that way, if this is true, if you divide this by n, the right-hand side goes like 1 over the square root of n, and it goes to 0 in the infinite system limit, so these fluctuations become very, very sharp. There's essentially no fluctuation. Okay. So that's what we know. Well, in active systems, you can actually show that the same quantity goes like n to some exponent a, which is bigger than 1f, and the theory, this kind of theory, will predict a is equal to 1 in 2 dimensions. So much bigger number of fluctuations that sort of makes statistical mechanics really no longer valid. And actually, these kind of fluctuations with an exponent of about between, say, 0.7 and 0.9, depending on the system, have been observed in things like material suspensions, layers of vibrated granular rods, certainly numerics as well. So it seems to be a real thing. So I guess the lesson here is non-equilibrium systems are strange. Okay? And if you want to learn more, I suggest you go to one of the reviews that I mentioned last time. Now, are there any more questions about this? Because I'd like to move on to my second topic, which is even simpler and also strange. But, yeah.
Well, you mentioned it. So is there any addition to this exponent now? I mean, is that
Yeah. So if you can calculate the density correlation function. Well,
is that universal, or is that just for the given model?
no. Well, so the equations are universal. If I don't tell you what the parameters are, I only tell you it's a system with ferromagnetic symmetry and it's an active system.
Pneumatic model.
Actually, the exponent comes out to be the same both for pneumatic and polar. For in 2 dimensions, the equation will give you 1. And in 3 dimensions, I forgot, but also bigger than, too big, essentially. I forgot the
And that means in order to verify the analytical predictions, what initial condition are we going to use? What
initial condition are we going to use if I want to do what?
To integrate numerically the system.
Hopefully any. Meaning, and people have done this, you could start with a disordered initial condition or with an ordered initial condition, and then depending on where you are with your alpha, if your alpha is positive, the system should go to a disordered state. If your alpha is negative, then the system will likely go to the banded state. Or for alpha, if you're deep in the ordered region, you might actually get. But you never get, a uniform state everybody traveling in the same direction. You always get this big number of fluctuations. So you always, what you see is a lot of clusters, essentially, in your system.
And how about boundary conditions?
Boundary conditions are important. So, for instance, if you have, well, first of all, to get to see a state where everybody is traveling in the same direction, you better have periodic boundary conditions. Otherwise, so in real system, boundaries in this kind of systems make a big difference. For instance, these particles, as we'll see in a minute, tend to accumulate at the boundaries if you have boundaries. But even if you have periodic boundary conditions, say in the simulations, then the shape of your box may actually affect, for instance, the type of bands you get and the orientation of the bands and things like that. So that's important. Okay. So, but I'd like to go to the second thing I want to talk about here. Where's the other one? Okay, there are 2 under the projector. Oh, here. So I'd like to tell you about a very simple model, which I think of it up as a model for active colloids, but actually it's sort of more general than that. And I think it highlights one of the features of this active system, which is really interesting. So I showed you a movie yesterday of these active colloids, these particles. In that case, were light activated. No light, then they go Brownian motion. And when light, then there goes something like the running tumble of E. coli. So I'm going to make a model of particles that have this kind of running tumble dynamics in 2 dimensions again, and see what they do. But before getting there, let me just remind you very quickly. So actually, Greg discussed random walks. Brownian motion is essentially random walks. We're just going to do it in a slightly different way because I'm going to do it through the dynamics. So imagine you have a Brownian particle. This is just a good old Brownian particle, large colloid in a fluid. It experienced a mean friction due to the fluid particle, and then noise due to the random collisions with the fluid particle. So I will write an equation of motion for such a particle. It has a mass m, So I write that the acceleration is equal to the net forces on the particles, which are friction and noise. I will call this noise eta of t. This is what's called thermal noise. It's due to these random fluctuations. And I'm working in 2 dimensions here. So this eta is a vector. And it has 0 mean. And it has correlations, which are, so it's uncorrelated in time. And its strength is related to kVt, which is a requirement of the fluctuation dissipation theorem. Because this is just an equilibrium system. So that's my model. This is called the Langevin equation. And that's how I describe the dynamics of this Brownian particle. Now, yesterday I said that over-damped dynamics means dropping this term. Just to make that a little bit more precise, there is a time scale in this problem here, which is m over zeta. I must have the units of time. So what I can say is that if I'm interested in times large compared to m over zeta, and of course if the friction is very large, this time is very, very small, so I will always be in that regime, then on this time scale I can indeed drop this term. And then my equation becomes simply zeta v equal eta of t. So now I have a Langevin equation for an over-damped Brownian particle. Okay? And I can actually rewrite it even more simply as, maybe I write it, actually, I want to keep some space. So let's go under here. So I had zeta v equal to eta of t, or I will write it as dr over dt equal to eta over eta of t over z. Okay? Now I will calculate the mean square displacement for this particle, which is, so first of all, if I calculate, I can trivially integrate this equation from some initial condition. It's simple enough, at least formally. So I will have that r of t minus r of 0 is equal to the integral from 0 to t dt prime eta of t prime divided by this constant zeta. This difference I will call delta r of t, which is the displacement from the initial position. And of course, if I were to average delta r of t over the noise, this bracket being an average over the noise, I get 0 because the mean of the noise is 0. But if I average the square, and this quantity is called the mean square displacement, what do I get if I average the square? Well, I have to write it as, say, integral 0 t, and maybe I call it dt1 eta of t1, integral 0 t dt2 eta of t2. They are dotted with each other. I have the 1 over zeta squared in front. And then I average over the noise, like that. The correlation gives me a delta function, okay? Then I have delta, Kronecker delta for the components, I have the strength of the noise, and when I do this calculation, what I'm going to get here, by putting in this quantity, I'm going to get 4 times kdt over zeta, because I have 1 zeta here, I have 2 zeta in the denominator, times t. What is this quantity? Diffusion coefficient. In Check dimension should be length squared over time. It's the diffusion coefficient of this Brownian particle. And the statement that d is equal to kt over zeta is the Einstein relation. Okay? So this is Brownian motion. And I could have actually got, if I actually had integrated my equations with the mass, a long time, I still would have gotten the same behavior. It would have just been quite a bit more work to do that. That's why I did this. Okay? So now, let's see what happens when you have what I like to call a self-propelled particle. And I need, of course, to tell you what is my model of a self-propelled particle. That is a particle that has a dynamics not unlike that of E. coli. So my model for self-propelled particle will be the following, although for this purpose I don't need a cipher. Imagine having a disk, so I'm in 2 dimensions. For simplicity, I could do it in 3 dimensions, or in 2 dimensions. Imagine having a disk, although for the purpose of calculating mean square displacement, you want to have only one particle. Whether it has a finite radius as a point particle clearly doesn't matter. But later on this will be important. That's why I consider a disk. I consider a disk, I will describe the dynamics, that's what I'm doing there, by the position of the center of the disk. Okay? But in addition, this disk is self-propelled. What do I mean? I mean, I identify an axis on this disk. So imagine that as is fixed on the disk itself, okay, has direction denoted by the unit vector, I guess I called it n yesterday, and the unit vector in 2 dimensions is just cos theta sine theta, where theta is the angle that it makes, say, with the x direction. And this particle has a fixed speed v naught along that direction. So v naught times n hat is what I will call the self-propulsion speed. Okay? In addition, there is noise. Noise does what? Well, there'll be noise on translational degree of freedom, there'll be noise on orientational degree of freedom. There'll be noise on the orientation degree of freedom is sort of rotational diffusion. And actually that would be the most important one, because I will eventually show that the translational noise is negligible in this kind of system. So let me write down the equation of motion for this particle, and let me do it in the overdamped limit. So something like this equation I have here, but I need to have the self-propulsion. Okay? So I'm going to write it this way. I'm going to write it as dr over dt. The friction is going to be brought to the other side, just like I did over there. And in fact, I'm probably going to incorporate the noise. So what do I have here? Well, I have self-propulsion. So I have V naught n. And then I have noise. And if you like, psi here is like eta over zeta over there. Okay? That's the thermal noise on the translation degree of freedom. But in addition, I must tell you something about the dynamics of the orientational degree of freedom. And I will assume that the orientational degree of freedom only experiences noise. So I will write this as theta dot, that's the derivative of the angle, is equal to rotational noise. Okay? And this rotational noise, I guess I should call it psi r, sorry. Let's call it psi r for rotation. This rotational noise is also with 0 mean and has correlations which are Gaussian and white, and I will call, let's see, what did I call it? So the coefficient here I will call it dr. dr is the coefficient of rotational diffusion, which unlike translational diffusion is actually a rate, as just dimensional 1 over time, and then I have a delta function in time. Okay. Now I would like to calculate the mean square displacement for this particle. If I calculate the mean square displacement for this particle, and I actually would like you to try to do the calculation as a homework. I will give you a hint in a minute, because it's actually, there is a trick to doing this. But if you calculate the mean square displacement for this particle, you can actually do the calculation exactly, and I'm going to write down the answer. We get something like this. 2v naught squared divided by the r plus d, where d is the one, sorry, I guess I need, okay, 4 v naught squared over 2dr plus d, okay, times, let me just, oops. Okay, times t plus e to the minus dr t minus 1 divided by dr. And this is something I calculate exactly. And of course, if you look at the limit for t large compared to 1 over dr, you can show that this becomes for something that I will call the effective times T, where the effective is this. Okay. Now, if so first of all, the dynamics a long time is still diffusing. And it is an effective diffusion coefficient, which is just the sum of the thermal diffusion coefficient, plus this sort of diffusion coefficient due to the fact that this particle performs ballistic steps at a rate v naught, randomized by the rotational diffusion at a rate di. Okay? If I actually put in some numbers, say numbers for E. coli. E. coli is like a colloid, it has a certain side, you know the friction. Or actually, even better, let me put in number for a real cycloped colloid, the particle about 1 micrometer diameter at a certain temperature. I can estimate the thermal diffusion coefficient, and I can estimate this quantity for this cycloped colloid. This part is about 100 times bigger than this part. So actually, I can always sort of neglect this part, which would mean I would have neglected these in my equation. So I have this really simple dynamics here for my self-propelled particle. Translational dynamics that just says that the velocity is the self-propulsion velocity, and then the direction of the self-propulsion velocity is randomized by rotational diffusion. Okay? This is what's called a persistent random walk. A long time is diffusive, but it has these ballistic pieces that last essentially a time 1 over dr. Okay? Now, seems rather innocuous difference, if you like, between these two types of dynamics. They're both diffusing a long time after all. But actually, it makes an important difference. And let me just spend the last few minutes, 10 minutes telling you one of the things that this different dynamics does. I'm going to erase this. Are there any questions? Can you think about questions while I erase? Now let me take a collection of these, again, my self-propelled disks, as I call them, and put them in a container, maybe I can call it. And, oh, actually, sorry, before, I want to point out one more thing. Notice that, so a long time the behavior is diffusive. If I neglect this D, I have a diffusion coefficient given by this quantity. Okay, now this is just the effective d naught squared divided by 2dr. Okay? It's very tempting to call this an effective temperature. After all, in thermal system, diffusion is kT divided by zeta. So it's very, very tempting to define an effective temperature by saying this is kT effective divided by zeta. And then ask, can we actually describe the dynamics of the self-propelled particles as just Brownian particles with just a much larger effective temperature? I said, after all, this is about 100 times bigger than that. And what I want to show you next is that the answer is yes, if you have only one, but definitely not if you have many. Okay? So now let's go look at many and see what they do. Because if we have many, we need to add some interaction. And the interactions I'm going to add are just steric effects, just repulsion, short-range repulsion. I'm not going to treat them as hard disks, actually, because when we worked on these originally, we had in mind this as a model of cells, and cells are soft. But other people have actually done similar models for hard disks, self-propelled hard disks, and the behavior they find is pretty much the same as we find for soft disks, so this is not going to really matter. But the kind of interaction we consider is soft repulsion. So we said, okay, if two disks overlap, so now I have many disks, so I can have two disks. When they overlap, say they overlap by some amount delta. Delta is the overlap of the disk. They will repel each other So this is disk I, this is disk J. They will repel each other like springs. So with a force that has a strength, some spring constant, this is not Boltzmann constant, this is a spring constant, proportional to that. Okay? And then let me write that, and they are over, but these are cyclopile disks. So this one may have its V naught N over Ni over there, this one instantaneously could have a V naught and J like that. Okay? So now let me write the dynamics for these cyclopile disks. Well, it's really very simple, so like before. There is self-propulsion, but now there is also interaction. So this is mobility, and I write this as sum over J, the force, the repulsive force. So whenever they overlap with some other neighbors, they experience this repulsive force. And then I have the dynamics for the angle. I will drop the R, since I'm not writing any thermal noise in there. I just have the rotational noise. And the correlation with the rotational noise are the same as given before. Okay, I have a label for the particles now, so maybe I should write it. And zero average, of course. Okay. So that is my model. Now there is at least one, so there are several parameters in this model. So I'm going to simulate these particles in a box, put them in a box and simulate them. And I will actually do two things. One, I will do it with periodic boundary conditions, and one, I will actually put them in a container. And I'm actually going to show you some pictures of what we find in a minute. But there are clearly some parameters. So one important parameter that is not there when you just have a single particle is the density. Or we actually want it in terms of packing fraction, phi, which is simply the fraction of the area of the plate which is covered by particles. So if the particles have a radius A, or we actually looked at polydispersed particles, again, because our original motivation was cells. And so in that case, it would be like the mean radius A, or actually you can calculate the packing fraction precisely. But let's just think of monodispersed for simplicity. Let's say they have a radius A. The packing fraction would be the number of particles, the area of one particle, divided by the area of your box. Okay? And disks like these will close pack at the packing fraction of about 0.1, I think. But they jam, meaning they all touch each other at the packing fraction of about 0.88. Okay, just as a reference for you to keep in mind compared to the numbers I'm going to show you before. So what happens if you put a bunch of these disks in a container, sorry, not in a container, with periodic boundary conditions, is that they phase separate. Okay? What does it mean they phase separate? I'm going to show you a picture. Let me show you the picture actually. And then, oh, I should have. I forgot. I was supposed to turn this on a little sooner. Now it will take a while, right? Push it once. Is that enough? Twice. You sure? Twice is to switch off. Are you sure it's twice to switch off?
You should see it come on.
Well, let's see what happens. The computer's there. Everybody's there.
There we go.
Okay, and the reason they phase separate is actually, you can understand it rather simply. Okay. Ah, what did it do there? I wonder. Okay, that's all right. All right. So this is a simulation of, I forgot how many of these disks, maybe it says somewhere, 10 to the 4 of these disks in some container. And what is shown here is, so the color shows the clustering, say. So particles that are touching each other are colored the same. And gray are isolated disks, green are clusters of a certain size, and so on. Okay. The right column like that shows my self-propelled disks at a packing fraction of 0.39 and 0.7. This other column over here shows what I call thermal disks. These are just Brownian disks. And I've chosen the temperature so that the temperature will, this disk on average have the same type of overlap due to temperature that my self-propelled disk will have to self-propulsion. So that's how I choose the effective temperature to compare. So as you can see, the thermal disk there is a bit of clustering at 0.7, but certainly the system is still very uniform. The self-propelled disks phase separate. That is, you really have a giant cluster which is solid-like. There is, I will show you a move in a minute, there is actually some motion in the system. Also, these were polydispersed disks. If they have been monodispersed, and people have done that now, you will see sort of a crystalline structure. But the particles are moving around. It's not really a real solid, and I think this is a movie. Does it play? Why not? Okay. So this is the cluster. Of course, we're using periodic boundary condition. To get the other picture, we actually patched it up to make a nice cluster in the middle. But the movie, we don't patch up. That's why you have the 2 bits. But it's really similar type of cluster. It's a single cluster. And you see, it's really a fluid. So it's a very dense fluid surrounded by a gas of active particles. Okay? And I'll tell you in a minute how you can understand this easily, but let me just show you one more surprising result. We have a phase diagram and we have things like that. I just want to show you one more result. If you put them in a box, what these active particles do is that they all go to the boundaries of the box. Again, here, these are my active particles. They were started in a homogeneous state, and then let go. And then after a while, provided the rotational diffusion is small enough, of course, that's a crucial parameter. This loop is looped, started again. They accumulate the boundary of the box. For comparison there is a system with a very large rotational diffusion which sort of behaves thermally, and the particles do not go at the boundary of the box. Of course, at very, very high packing fraction, I think this is of the order of 0.9, as a matter of fact. They cannot all go to the boundary of the box because there's just too many of them. And so they actually jam, but they're still capable of making sort of holes here and there by overlapping with each other. So this tendency for these self-propelled particles to sort of cluster and have these large density fluctuations is present even in this very, very simple system. And is actually ubiquitous in things like bacterial suspensions or these self-propelled, well, you saw the self-propelled colloids that were making these crystalline clusters when they were activated by lights. We have actually also looked at the equation of state for these systems, calculating the pressure, and I don't really have time to go through that because I want to give you 1 minute argument to try to understand why this happens. And that is actually very strange as well. But somebody asked me after, I can tell them. So let me just actually spend 1 minute now telling you how one may be able to understand that very simply. I need to switch this off. There. I know I'm almost over time, but this is really a 1 minute time. So what's happening in this system is actually something which we actually know. We are familiar with the idea that, where don't the lights go? We're familiar with the idea that if you have a density fluctuations, we're familiar with diffusion. Diffusion tends to make density equal everywhere. I have a high density over here of something, particles will diffuse, the equilibrium system is the one where the density is uniform. That seems like normal, right? That's what happens. On the other hand, actually, what's happening for this particle is something that is, I think, almost even more intuitive, as a matter of fact, which is simply that particles, self-propelled particle, will accumulate in the region where the velocity is lower. So the density is high where the velocity is low. And the steady state, as a result, if there are variations in velocity, the steady state is not one of uniform density. Or another way to say, just think about it, these particles are self-propelled, but when there are many of them, and they can get caged, they have to slow down. And the more they slow down, the higher the density in that region will be. And this essentially leads to accumulation of particles in regions of low velocity and to this kind of phase separation of large amount of clusters. A slightly more technical way of saying that is that what these systems doesn't have is what in equilibrium is called detailed balance. That tells you that if you have flux from, if you have a different in density between right and left, flux from right to left has to be equal to flux from left to right until the system goes to the state of uniform density. But if right and left are self-propelled particles with different densities and different self-propulsion velocities, then the equilibrium state will not be one where the density is uniform everywhere, but will be one where the density is higher, where the velocity is lower. And then you can actually make simple models, especially in one dimension, and get exact solutions for this system, which show you precisely that. So again, we are used to think about that, okay, equilibrium is where density is constant everywhere, but actually the idea that things accumulate where velocity is low is even more intuitive in my mind than the idea of equilibrium. And that's really where a lot of these effects come from. So I'm going to stop here because I'm out of time. But if you have any questions or if you want to learn about pressure, I can also just come up to me later because I think we have to go on to the coffee break, I guess. Or we go on to the coffee break, I would say. But if there is any question. Any quick question I can answer now, or with coffee, as you prefer.
Right. Maybe not a quick question, but in this last set of simulations, and maybe there's some way to study it analytically, is there a critical cluster size below which is unstable? I mean, are there other sort of... So there's some...
You're talking about the phase separation?
Yeah, so is there some cluster which is too small to support...
It's really like spinodal decomposition. It's not like nucleation.
Okay.
And we have actually constructed we and others have constructed a phase diagram and tried to see if we can really understand this behavior until a critical point. And
so every wavelength is
yes, yes, that's right. There is a region where, but this is really more like spinodal decomposition, and so I don't have.
Okay.
Yeah, and well, maybe as a teaser, I'll show you the pressure if I can find it. Ah, that's the pressure as a function of Pekin fractions. Projector is on. Okay, forget it. Point is, pressure is non-monotonic. Pressure is function of Pekin fraction, which is measured by measuring in the closed box by measuring the force on the boundaries. But we also have an analytical expression that actually reproduces it. First goes up with density, but then goes down. Well below jamming, and then actually shoots up again at 0.9 because then it does that. And it looks so much like a Van der Waals curve that is. So, anyway. Okay, thank you. Let's have coffee. I guess I should erase